We'll continue our discussion of probability, and in section 8.1 we'll start by talking about empirical probability, or another name for it would be experimental. In other words, we're going to be paying attention to what happens after we do some sort of experiment, such as rolling a die or drawing from a deck of cards. And that empirical probability is found by taking the frequency that the event we want occurs and dividing it by the total number of trials that we did. So, for example, if we were wanting to toss a coin and we were talking about the number of heads that we would get out of 8 tosses, our empirical probability would be 3/8 if we get heads 3 times out of 8 tosses. Now, theoretical probability is different. That would be looking at the number of possible outcomes that can occur, the number of ways it can happen would be in our numerator over the number of elements in our set, the number of different things that can happen on an outcome, such as if I just ask what's the theoretical probability of getting a heads when I flip a coin, well, for each flip of the coin, I have one chance of getting heads out of 2 different sides, 2 different outcomes that can occur. So the theoretical probability of getting heads on any flip is 1/2. So that would be important to note the difference between these two. And now we're going to look at some experiments here. And we want to find the probability of drawing, in number 1, a black jack out of a deck of 52 cards. So what I do know is that I'm going to get the probability of getting a black jack out of a deck, and that's going to be my numerator, divided by the number of cards in the deck for the denominator. Well, if you remember anything about decks of cards, we have 4 suits, 2 are red and 2 are black. So I have clubs and I have spades that are black, and each one of those would have a jack. That means there are 2 black jacks in a deck of 52 cards. Now, that fraction can be reduced down. So simplest form is 1/26, and that would be my probability. Now, if I ask you what's the probability of getting the ace of spades, well, there is only 1 ace of spades in a deck of cards out of 52 cards. Nothing to reduce there. The probability is 1 out of 52. Now, what if I ask you what's the probability of getting an 8? Well, you have to decide how many 8s are in a deck of cards. Well, we said before there are 4 suits. Each one has an 8. So that means I have 4 out of 52 cards that would be an 8. Now that fraction reduces. Both of those are divisible by 4, and I end up with the fraction 1/13. And then the probability of getting a 6 is going to be the same as we just got when we asked for the probability of an 8. There are 4 6s out of 52 cards, which gives us a probability of 1/13. Now, if we look at number 5, we have something a little bit new here. And what it's asking for is a probability of getting a 6 of hearts or a 6 of spades. Now, anytime you see or, an or statement with probability, it's asking you to add these 2 probabilities together. So you want to make sure you remember that. And the probability of getting a 6 of hearts, I know there is only 1 6 of hearts out of 52 cards, plus there's only 1 6 of spades out of 52 cards. And that means I get 2 out of 52 when I add those up, which would be 1 out of 26. And then the last one, we need to think carefully about the easiest way to come up with this one. Since we want a card that is not a black 6, pay attention to that word not. The easiest way to calculate this is to take the complement. That would mean that it's going to be finding the probability that we would have a black 6, and then we subtract that from 1, because remember, 1 is 100%. If we get a probability of 1, it's everything that's been counted up. So if we take 1 minus the probability of a black 6, that means I have 1 minus, now the probability of a black 6, there are 2 suits that are black. Each one would have a 6 out of our 52 cards. So if I get a common denominator, that would be 52 over 52 minus 2 over 52, which gives me 50 over 52, which would reduce down to be 25 over 26. So a very high probability that I would not end up with a black 6. Now, this next example will review the fundamental counting principle, which we did talk about in Chapter 7. Remember, we said we can put a blank for each choice that needs to be made, and then we can come up with the outcome that we're looking for. So if we're purchasing a new car and we have to make these choices, we're going to either choose a Ford, a GM, or a Honda. We want to choose either a compact or a midsize, and we have either white, red, black, or green for our colors to choose from. We want to know how many different ways we could select one manufacturer, one car size, and one color. Now it says use a tree diagram to check your result, but we don't need to do that. Instead, we know we're going to be choosing a manufacturer, we're going to be choosing a car size, and we're going to be choosing a color. So I'm going to put down 3 blanks, and if you remember with our fundamental counting principle, we're going to be multiplying together how many of these choices we have in each blank to get our total number of ways we could select this car. So the number of manufacturers to choose from is 3, because it's Ford, GM, and Honda. My car size, I have 2, either compact or midsize. And for colors, there's 4. White, red, black, or green. If I multiply that together, I come up with 24 ways I can select the car. Now, to find probability when we're using the counting principle, we're going to do the same thing as far as make those blanks, and we'll be multiplying together what we put into the blanks, but we're actually going to answer the question, what would be the probability of, in this case, getting your college ID number if you're randomly generating 8 digits. So since our college ID consists of 8 digits, I'm going to have 1, 2, 3, 4, 5, 6, 7, 8 blanks. I know I'm going to be multiplying together whatever goes in each of these blanks. And here's what it tells me. Each digit can be 0 through 9, and each digit can be repeated. So if I count up how many digits there are from 0 through 9, that's actually 10. And since there's not a restriction on repeating digits, that means even if I pick a 1 for the first digit, it's still possible to pick 1 for the digit that comes after that. So since these are completely independent events, it means I'm going to have a 10 in each of these blanks because I have a choice from 10 different numbers every time this gets generated. Now, that just multiplying this together gives me the total number of different ways that or different numbers I can come up with for the college ID number. And that means I'm going to have a 1 with 8 zeros after it. 1, 2, 3, 4, 5, 6, 7, 8 zeros. Look at that. That's 100 million. And that's how many different numbers can be generated. But here's the question. What would be the probability of getting your college ID number when you randomly generate these digits? Well, think about it. Out of all of those numbers that get generated, how many of them would be your number? Only one. You have a 1 out of 100 million chance of randomly generating your college ID in this scenario. Now, let's look at this. Go back to the cards. We're going to deal 4 cards from a standard deck of 52 cards, and we're going to find the probability of being dealt a certain hand. Now, to help us out a little bit, we are going to need to know something about combinations, and there are a couple of things. For instance, when I teach statistics, we talk about this in greater depth. Let me just give you a quick explanation. You have permutations and combinations, and I believe we did review this a little bit back in chapter 7 as well. But just in case it's been a little while, let's talk about this. When it's a permutation, order matters. We talked about if you had a lock, it's oftentimes called a combination lock, but that's really not named correctly because the order you put those digits in and the direction you're moving makes a big difference on whether or not the lock would open. It really is a permutation lock because order matters. In a combination, order doesn't matter. And what we have here is the denominator they're giving us. They've done the work for us to determine the number of different 4-card hands you could end up with if you're dealing out of a deck of cards. And you find that because order won't matter. That's what makes it a combination. And out of 52 cards, you're going to get 4 of them. So that's why we see this right here. We're taking a combination of 52 things, taken 4 at a time. That gives us this denominator of 270,725. That's how many different 4-card hands could be dealt out of that deck of 52 cards. So in order to find the probability of getting a hand that has 4 kings, this is what you will have to stop and ask yourself, okay? Out of those cards, would order matter on getting kings? Absolutely not. And if I'm going to get 4 cards and I want them to all be kings, what I'm finding is the order doesn't matter. That's a combination. But I am wanting to choose from 4 kings in the deck, and I want all 4 kings in my hand. That's a combination of 4 things taken 4 at a time. If you either put that in the calculator or you do it using the formula to calculate a combination, and even if you just think about this, there is only one way you can get 4 kings in your hand, because that's all there is in the deck of cards is 4 kings. That means the probability of getting 4 kings in that hand is 1 out of 270,725. Not a very good chance. I would not go to Vegas and bet all my money that I'm going to get 4 kings whenever you deal that hand to me. Now, on number 8, we want the probability that we would get 3 aces and 1 king. Now, this one, you got to think a little more carefully because it's still a combination. The order I get these in won't matter. And if I'm wanting 3 aces, it means there are 4 aces in the deck. I want to choose 3 of them. So I've got a combination of 4 things taken 3 at a time. Now, I need that and 1 king. And if you remember, we said when you see or, it tells you add probabilities together. When you see and, it means you multiply probabilities. So we're going to have to multiply that times wanting to know if, again, it's a combination because the order doesn't matter, but to get 1 king, I'm going to choose from 4 kings in the deck. I just need 1 of them. So I've got to get a combination of 4 things taken 3 at a time times a combination of 4 things taken 1 at a time. If you were to compute those probabilities, put them in your calculator, you would come up with 16. You would come up with 16. And that means you have 16 over 270,725. That's not a very high probability either, but it is much better than just getting 4 kings. Now, think about this. I want the probability that I get no aces in my hand. Well, to calculate that, it's still a combination. But if I want no aces, ask yourself, that means how many cards are not aces in the deck? Well, there are 4 aces. 52 minus 4 is 48. So I've got 48 cards I can choose from. How many will I need in my hand? 4. So it's a combination of 48 things taken 4 at a time. Again, and if you don't remember where to go in the calculator, I should have mentioned this earlier. Just to remind you, if you're looking for this, you can go into Math, which there is a button that says Math. You arrow over to where it says PRB for probability. This is if you're using the TI graphing calculator. And then you can find the one that says this. Now remember, you have to enter the N first before you hit that button for combination. Then you type in the R. So if you put this in your calculator, you get 194,580, which means if I want the probability of no aces, that's 194,580 over that denominator they gave us, 270,725. Now this is a pretty strong likelihood because if I compute this out and get a decimal number, that's 0.7187. So you got about a 72% chance you wouldn't get an ace anyway when you're dealt a hand. Now, to get the probability that you only have face cards in your hand, again, order won't matter, so that makes it a combination. Now, ask yourself how many face cards are in a deck. Well, all 4 suits have a jack, a queen, and a king. So 3 times 4 means there are 12 face cards in the deck. I want to choose 4 of them. So a combination of 12 things taken 4 at a time will give you a value of 495. So the probability of only face cards is 495 divided by 270,725, which is about 0.0018. That's a less than 1% chance. Again, I would not go to Vegas and bet the cash in my wallet on that happening. Let's look at the next example. Now let's talk about rolling some dice. So we're going to roll 2 fair dice. We're going to add the dots on the 2 sides facing up and assume that each simple event is equally likely. In other words, these are fair dice. They're not weighted to where one side is more likely to turn up than another. And we want to find the probability of the sum of the dots that are indicated in these problems. Now, I will tell you, it is possible to compute these without drawing a little grid or table to help you out, but I think you're going to find anytime it's asking you about the probability of the sum of dots on a die, on 2 die, I would do this. I would draw a 6 by 6 grid. So I'm going to make 6 columns and I'm going to make 6 rows. Okay, and what I'm going to do is number across the top of each column and down the side of each row what the possible outcomes would be for each die. So if I'm rolling, I could have a 1, a 2, a 3, a 4, a 5, or a 6, and I'll put that beside each row as well. So before we start, let's add up what we would get on the rolls and put the sum in the box where they intersect. For example, if I roll a 1 and a 1, add those up and I get 2, so that goes in the top left box. 1 plus 2 is 3. 3 plus 1 is 4, and so on. So we're going to fill this thing out. And then we come to the next row, and if I get a 2 and a 1, when I add those up, that's a 3. You will notice there's a little pattern as you start to fill this in. If I add a 3 and a 1 on row 3, that gives me a 4. So this row will be 4, 5, 6, 7, 8, 9. If I have a 4 and a 1 on row 4, that means I get a 5. And then we'll continue counting up by 1 all the way across this row. 5 plus 1 is 6. This is just going to make it a lot easier for us in a minute when we need to add up these probabilities. 6 plus 2 is 8, 9, 10, 11, and then in the last box we'll have the number 12. Okay, so if I draw this out, one thing I know for sure, there are 36 outcomes in this grid because it's a 6 row by 6 column. So all I have to do is count up how many times does 8 show up as an answer. Well, if you will look, you're going to find the number appearing on the diagonal. Right here is the diagonal where the 8's are. And if I count them up, I have 1, 2, 3, 4, 5. So I have 5 times I get an 8 out of 36 possible outcomes. That's all you got to do. So if I ask you how many times would I get a 7 for the sum, look for the diagonal that has the 7's, and if I count those up, there are actually 6 of them. And 6 divided by 36 reduces down to be 1/6. I have a 1 out of 6 probability that I'm going to get a 7 when I roll those dice. That looks like that would have to be the most likely event to occur if I'm just talking about what number could I get if I add up the dice. Look at 13. It says, what about the probability that the sum is not 7? So what I want to figure out is it can be anything but 7. That means I could go through and I could count all those other numbers, but remember, sometimes the complement is the easiest way to find it. This is the same as 1 minus the probability that you do get a sum of 7. Well, we just found that. The probability of getting a 7 was 1/6. And since we need a common denominator, we'll write 1 as 6 over 6 minus 1 over 6. We have a 5/6 probability that we won't get a 7. All right, probability that the sum is divisible by 4. Now that means I need to count up how many times I get 4, because 4 times 1 is 4. 4 times 2 is 8. And if I do 4 times 3, it's 12, and I actually see that in the table too. And that's the largest number in my table, so I know I don't have to go any higher than that for multiples of 4. So let's count up and see what we see. We have 1, 2, 3 times that we see 4. Looking on the diagonal. So 1, 2, 3. Our 8 occurred 1, 2, 3, 4, 5. So 3 plus 5 is 8. Plus the 12 means I have 9 out of 36 that I have counted from the table. What I did is count up how many were 4s, how many were 8s, how many were 12? When I added those up, I got 9. And 9 out of 36 reduces down to 1/4. There is a 1/4 probability I'm going to get two numbers that when I add them up, the sum is divisible by 4. Now, to calculate how many of these numbers the sum is odd, well, that means I've got to count up how many 3s, 5s, 7s, 9s, and 11. Count those up, and you're going to see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 out of 36. Now, is that kind of logical when you think about it? It should be. Half of the time the sum will be odd, which would mean half of the time the sum is even. And if I counted up even, I would also come up with 18. All right. What is the probability that the sum is greater than 1 and less than 13? Well, look carefully at that table. How many of these numbers are greater than 1? All of them. How many of these numbers are less than 13? All of them. The probability of that happening is 1, because there isn't anything in the table that doesn't meet both of those conditions. So that would be fairly simple if you just think about it. All right, on 17, a Mathematics 110 class at a junior college must select 3 students to serve on an advisory committee to the dean. There are 14 freshmen, 12 sophomores in the class. So, question number 1, how many 3-person committees can be chosen from the class? Now, ask yourself this question first. Is it a permutation? Does order matter? Or is it a combination and order doesn't matter? If you're putting together a committee and it has Fred and Sam and Mary on it, does it matter the order I put their names down on the paper if all I'm doing is listing who's on the committee? Honestly, no. It's just those 3 people form the committee. No, it doesn't matter what order their names are in. That means this is a combination. And since it said how many 3-person committees can be chosen from the class, that means I need to know how many people are in the class. And if you look at this, there are 14 freshmen, 12 sophomores. Altogether, that means I am choosing from 26 people. And how many people do I want on the committee? 3. So this is a combination of 26 things taken 3 at a time. Imagine this, there are 2,600 ways that I could put together a 3-person committee. That's how many different committees you could get out of 26 people. Kind of crazy when you think about it. Now, how many 3-person committees could be chosen from the class if the committee consists of only freshmen? Okay, it's still a committee, so order doesn't matter. That means it's still a combination. But what am I choosing from now? Only freshmen. And how many are freshmen? 14. And how many am I going to put on the committee? 3. So if I'm choosing a combination of from 14 things taken 3 at a time, 14 people, I'm going to choose 3 of them. I now only have 364 different committees that could be formed. So it drops considerably since we're only choosing from 14, which is a smaller number than 26. How about if it's only sophomores we choose from? Well, that's going to narrow it a little bit more because according to our information, there are only 12 sophomores in the class. So we're going to take a combination of 12 things taken 3 at a time, do the number crunching on that, and you find out there are 220 different committees that could be formed just using the sophomores. All right, last question on this says, how many 3-person committees can be chosen from the class if the committee has 2 freshmen and 1 sophomore? And pay close attention to the word and, because that's going to tell us what operation we're going to need to do with this. We actually have 2 different combinations we have to calculate here. we're going to get, if we're choosing 2 freshmen, that means it's a combination. We're choosing from the 14 freshmen, but we're only going to pick 2 of them. That's going to be the ways that I can come up with the number of freshmen. The number of sophomores, it's still a combination. I have 12 sophomores I can choose from, and I'm only going to pick 1 of those. And if you remember, when you see the word and, you have to remember to multiply those together. Or means add, and means multiply. And if I do that, I'm going to come up with 1,092 different ways that that committee can be formed.